An aluminum dog bone specimen is instrumented with a rosette strain gauge to measure strain. The rosette gauge consists of 3 uniaxial strain gauges oriented at 45-degree increments. Since the rosette is mounted at an oblique angle to the primary axis of the aluminum, Morrow's circle is required to determine the principal strains. For replication, all the ME395 GSIs have measured the width and thickness of several aluminum dog bone specimens using a digital caliper and micrometer. An Excel spreadsheet will be provided on Canvas containing all the recorded values. The lab has 2 Instron testers with a central computer console to interface both machines. For the tensile test, we'll be using the 8516 on the left. Before calibration, verify the load cell is unloaded with the grips empty. Press the setup button below the flashing green LED. On the lower console, press the soft key sequence Cal, Cal, Auto, and then Go. The LED will begin to rapidly blink during calibration. When calibration is finished, the LED will glow steady. Next, the load cell must be balanced or zeroed. As before, press the setup button for the load channel. On the lower console, press the soft keys for Cal, Cal, and Balance. The load display should now read about 0. Press button 1 to start the hydraulic pump in low pressure. Wait several seconds before pressing button 2, which jumps to high. On your desktop, open the X95 shortcut folder and select Aluminum Tensile Test with Morrow's Circle. Once the program opens, navigate to the Configuration tab. The title and sampling frequency may be edited, but the defaults should be sufficient. The LabVIEW offsets are used to zero load and position. On the configuration panel, set both offsets to 0. Select the Take Data tab to open the front panel and start LabVIEW. Click on the green Take Data button and note the average value for both load and position. When done, click the Stop button and cancel the prompt to save the data. Return to the configuration panel. Now enter the load and position values as offsets, but use the opposite sign to force a 0 reading. Now return to the front panel and click Take Data. Load and position should now read about 0. Before proceeding, let's verify all 3 strain gauge channels are operational. Plug the rosette connector into the white box. In LabVIEW, null and then calibrate the rosette strain gauge. Click the Take Data button and manually stress the dog bone specimen. All 3 channels should be responsive to the stress. If not, get another dog bone specimen. After validating the rosette gauge, install the dog bone specimen into the grips. Only tighten the upper grip and leave the lower grip open for now. The load cell needs to be balanced again to negate the mass of the specimen by pressing Setup, then Cal, Cal, and Balance. In LabVIEW, null and then calibrate the rosette strain gauge. Press the Take Data button to begin data collection. Now tighten the lower grip of the Instron and notice a preload is imposed on the specimen along with the corresponding strain. On the Instron, press the Start button. The applied load should immediately start to climb as the RAM begins to move. Click on the tab labeled XY chart for a better visual. Load versus displacement is plotted in white, load versus strain in red. Looking at the graph, notice the displacement axis is along the bottom, with the strain axis along the top. The lower grip of the instron is connected to a hydraulic cylinder, which is moving at 0.04 millimeters per second to gradually increase the applied load. The material properties of many materials are highly sensitive to the rate of loading. Plastics and steels exhibit significantly higher tensile properties under higher rates of loading. For that reason, testing must be performed within the limits of a specified governing body, such as ASTM. As an interesting note, aluminum alloys are actually fairly insensitive to the rate of loading, but we're still going to test this specimen at a low rate. Looking at the strain versus load plot in red, the straight linear curve indicates the specimen is currently in the elastic region. At around 50 kilonewtons, notice the knee in the curve, or the inflection point, as the specimen transitions into the plastic deformation region. Unlike the brass tensile test performed earlier in the term, notice how the applied load remains relatively flat for the remainder of the test, which indicates the material cannot be cold worked in the same manner as the brass was. Eventually, the strain channel will drop as the strain gauges begin to fail. Toggle the Enable switch to discontinue plotting strain. Then we'll switch to the front panel to view the 3 strain channels and the sequence of failure. From this point forward, strain is calculated by establishing a relationship between strain and displacement within the plastic region up until the first strain gauge failed. This relationship is used to extrapolate all future strain values based on displacement. Finally, the last strain gauge visibly failed. Let's return to the XY chart. Although the last strain gauge just dropped off, the erratic green curve towards the end suggests the gauge probably failed earlier. Looking at the load displacement curve in white, the load appears to have peaked. You'll notice the load will slowly begin to drop until the specimen ultimately fails. Once failure occurs, the test is finished. In LabVIEW, navigate to the front panel and press the Stop button to discontinue data collection. Save the data to a tab-delimited text file for analysis. Here is a view of the data opened in Excel. Load and displacement are listed in the first two columns, followed by the three strain measurements. Mohr's circle is utilized to calculate the principal strains in the axial and transverse directions.